Hi, welcome to Lumora University. My name is Snigdha, and today I'm going to be teaching oscillations. Specifically, I'm going to be talking about the derivation of the time period formula. So before we start, we can look at a diagram of a spring over here. One end of the spring is attached to the wall, and the other end has a mass m attached to it. And let's assume that this spring is moving in simple harmonic motion, meaning that it's going back and forth, and we need to find the time period of that spring. And this spring has a spring constant of k. Okay, so first we're going to go to Newton's second law of motion, which tells us that the sum of all forces in a system is equal to the mass multiplied by acceleration. Okay, and now we need to think, what is all the sum of all the forces in this system over here? Because it's moving in simple harmonic motion, everything is an ideal situation, and the only force present over here is the restorative force. And in this case, the restorative force is the spring force. And a law that explains more about the spring force is Hooke's law. Okay, so Hooke's law tells us that the spring force F is equal to minus kx. So in this case, since the spring force is the only force present, it is sigma F, so we can say negative kx is equal to ma. And when we're solving for the time period, for now we're trying to solve for everything in terms of a. So over here, I'm going to isolate a by dividing on both sides and say minus k over m multiplied by x. So this is our equation for a. Let's define this as equation 1 so that it's easy to remember. Okay, and now what we're going to do is we're going to focus on a main equation in oscillations, and that is x of t is equal to a cos omega t. Okay, so what this equation is telling us is it's representing the position of mass m at any given time t in this motion over here. And that is given by the equation x of t is equal to a cos omega t. And as I said before, we're trying to solve for the acceleration to find the time period. So over here, we know that the derivative of x of t with respect to t is velocity, and then the derivative of the velocity with respect to t is the acceleration, meaning that the second order differential of x of t is equal to a. So first, let's do the first order differential, which is dx of t by dt, which is equal to minus a omega sine omega t. Okay, and now we're going to go further and try to get a by doing d square x of t by dt square, which gives us, we just differentiate this one more time, and we get minus a omega square cos omega t. Okay, and now we know that a is equal to d square x of t by dt square, which gives us minus a omega square cos omega t. But what I'm going to do now is I'm going to simplify this a little further using our original equation over here for oscillations, which is x of t is equal to a cos omega t. Okay, so first thing I'm going to do is I'm going to take out minus omega square. Okay, so it's going to become clear y in a few seconds. And then I'm going to say a cos omega t right here. So now if you look back at the equation we had for x of t, we know that we can substitute that over here to get that a is equal to minus omega square x. Okay, and we can say that over here, and we can say this is our equation 2. And now we notice from equations 1, and so we can see over here, equation 1 and equation 2, that both of them are equations for A. So now what we can do is that we can equate them to each other. So now we can say equating equations 1 and 2 minus k over m Okay, so minus k over mx is equal to minus omega square x. And now we're trying to solve for omega. So first thing we do is we divide by -1 on both sides to get k over mx is equal to omega square x. And now we divide by x on both sides to get that k over m is equal to omega squared, giving us the final equation of omega is equal to square root of k over m. Now let's define this as our third equation. Okay, so omega is our angular frequency, and we solved for it in equation 3 to get a final value. And now I'm going to introduce another equation from oscillations that defines omega as omega is equal to 2 pi f. Okay, so now when we're manipulating omega, we're trying to solve for an equation that gives us t in terms of omega. So the first thing that we can do over here to substitute t is notice that f is equal to 1 over t. Okay, so you might be wondering why is f is equal to 1 over t and why is t equal to 1 over f? So first of all, frequency it tells us first of all, its units is in hertz, okay? And it tells us how many cycles can the motion or the mass in SHM make in 1 second, and the time period t tells us how many seconds it takes for one cycle to happen. Okay, so that's why they're the reciprocal of each other. So using that information, we substitute for omega to get 2 pi over t. Okay, so now we're going to isolate again for t, because after all, we are solving for the time period of a spring. So we say t is equal to 2 pi over omega. Okay, so now we can use, let's say we define this as our equation, so let's define this as equation 4. Okay, so now we know that equation 3 is our equation for omega, and equation 4 is our equation for t. So that means that we can substitute equation 3 into equation 4 to further simplify our equation for the time period. Okay, so let's undo that. Okay, so now we get t is equal to 2 pi divided by square root of k over m. And now we can do some algebra to get our final answer of t is equal to 2 pi multiplied by the square root of m over k. So this is our final equation for this time period of a spring, and the main thing to notice from this derivation is that it is extremely important to focus on the basics, which are, we started from Hooke's law and Newton's second law, and that further emphasizes that a good understanding of the basics leads to a better understanding of the more complex stuff in AP Physics or a physics course in general. Thank you so much for listening, and